Alright, we got the beginning of Unit 5 here. We're going to be talking about mid-segments, and then we got two new properties, I guess, for perpendicular bisectors and angle bisectors. So anyways, mid-segment of a triangle, that's kind of new here. I guess that's going to be a segment connecting the midpoints of two sides of a triangle. So if you look down here, this would be a mid-segment here, DE. I'm going to get a different color going here. Alright, and we got a couple of theorems we'll talk about here in just a second, but that's what a mid-segment is of a triangle. Perpendicular bisector, we've seen that before, we've constructed that before. That's a line or ray segment that intersects a segment at its midpoint, and it forms a right angle. Also, you got the angle bisector while we're on that same topic there, a ray line or segment that cuts an angle into two equal angles through its vertex. Alright, and then we're also going to use this word a little bit, equidistant, same distances to a common point or object. So anyways, here's the mid-segment theorem. The segment containing the midpoints of two sides of a triangle is equidistant, or I'm sorry, it's not equidistant, is blank to the third side. We're going to say it's parallel. And then also it's going to be half as long as that side. So DE right here is going to be half as long as the AC segment right there. So parallel, and then DE is 1/2 AC. Alright, now actually I wrote out a formal proof for that since we've been talking about proofs a lot lately. I wrote out a formal proof, but I'll put that at the end of the lesson just in case you're not so concerned about seeing the proof. So anyways, what are the three pairs of parallel segments in DEF? Because we have a bunch of mid-segments going on in a bunch of different directions. So I guess if I start out with BC, looking at that, we're going to say BC, that is parallel to the mid-segment DE. Okay, now if I switch gears and talk about maybe the side BA. BA will be parallel to the mid-segment over here, so that should be EF. And then I guess the last set would be AC. It's parallel to DF. Okay, so that's pretty straightforward there as far as listing out the parallel sides. Usually y'all do good with that, so not a big deal. Alright, now MP is the mid-segment of triangle LNO. Find the value of X. Let's check this out here. This side needs to be half of your biggest side right there. So we need to go do 16 divided by 2. That's 8. So that's what X equals there. Super easy. There's really, not a whole lot going on with those. I think I'm going to add in an extra example here at the bottom. But anyways, this next one here, notice they give us the mid-segment, so we got to think backwards. We got to go and take your mid-segment and multiply it by 2 to get the side of the triangle ON. So that'd be 14 right there. Now, every now and then you'll see examples where they'll give you the mid-segment. I'm just kind of doing a rough sketch here. And they might do something like this. They might say this side here is like X plus 7. And then they might say, the second side, I don't know, it's like maybe 3x. I'm trying to make this up in my head to where it'll work. Or here, let me do it. Even number 4x, and then plus, I don't know, 20 right there. So, anyways, the whole idea with these, and I'm not sure if the numbers will come out exactly the way they're supposed to, but the whole idea for setting this up is you want to either say that this side, if I do 2 times the mid-segment side, that should give me the opposite side. Or you could say 1/2 of the big side that you have of the triangle. You can say 1/2 of that equals the mid-segment side. It doesn't really matter. So I'm going to write it in 2 different ways here. You can say 2 the small side, 2 times the small side equals the big side. Or you could go and say the small side is half of the big side. And I'm not sure if this thing will come out clean because I just kind of made it up in my head because I forgot we didn't have one like this. So anyways, I'm going to work the first one. You can go work the second one if you'd like. That'll be 2x plus 14 equals 20. Oh yeah, you see I messed up the numbers here, so and that's going to be okay. We're just going to get a negative number, I believe, for our x value. So I'm going to subtract over the 2x and actually wind up getting 2x, and also go minus 20. So I guess that's negative 6, and then x equals, I guess, what is that? The negative 3. Actually, you know what? This might actually work out. So the whole idea, when you plug something back in, you don't want negative distances. But actually, if you plug in negative 3, you should get 4 up there. And then you should get, I guess, 8 down here at the bottom. So it actually does work out when you plug the number itself back in. But that's how you would set up one that's got more of the algebraic approach, because I think the textbook has a few of those. Bottom line, though, the mid-segment is 2 times that. Gets you the longer side, or you could think of half of the longer side gets you the mid-segment. That's really it. So those are pretty straightforward. Just watch out for the ones where they got the algebraic expressions. Those are a little tricky there. So I guess we have a window here. A large triangular window is segmented as shown in the diagram. DF and EF are mid-segments of ABC. Find DF and AB. So we want DF and the whole side AB. So AB should be easy because we already have the mid-segment right here. And remember, if we double the mid-segment, we go and get the side across from it, the side of the triangle across from it. So that'd be, whoops, not 90 degrees, I guess 90 inches. And then I guess we also need to find DF. So it's kind of like the same thing here. You start out the long side and then do half of that. And then I guess you get 45 inches right there for the mid-segment. So I guess it happens to make a couple of isosceles triangles there. So anyways, that is it about the mid-segments. Now this next theorem here actually kind of erased a few little things here because I wanted to talk about what this theorem means and why it's true based off of what we've learned in the past here. So in a plane, if a point is on the perpendicular bisector of a segment, then it is blank from the endpoints of a segment. Okay, so imagine you went and did your constructions and you did your thing where you got your perpendicular bisector. And you did that, and then choose a random point. So I guess in this case here, they choose C as a random point. Well, what we're going to say, we're going to imagine that we have 2 lines that connect C to the endpoints of your segment there. Based off of what we learned, we can prove that these 2 sides happen to be congruent, but we don't know for sure yet. Okay, but based off of the picture and what we know, thinking back to last unit here, notice that you have a shared side. We know that this has to be a right angle because we made it to be a right angle. We did a perpendicular bisector, and then also therefore these 2 sides are congruent. And because you have 2 congruent triangles there, you have 2 congruent triangles because of side angle side right there. That means everything else about the triangles, the 2 triangles, are going to be congruent. That means the rest of the angles, the rest of the sides as well. So that means AC is the same distance as CB. Okay, so we can go and fill in this equidistant word. C is equidistant from the endpoints of your original segment right there. So we can go say CA is equal to CB, whatever those measures are right there. And that's because of side angle side right there. You don't necessarily need to know the side angle side, you just need to know, hey, if you got a perpendicular bisector, these segments connecting should be the same. All right, and that's based off of your side angle side. Now you also have the same thing that's basically the converse of that. In a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. All right, and the reason this one kind of works out, I guess, is let's say, I guess they're saying that C is the random point that's on there. All right, what you got to remember is when you say you have like a random point C and you're trying to find the distance, I guess from a line, we always say that distance is perpendicular when you're going from a point to a line. We take that shortest possible distance, and that shortest possible distance is always perpendicular. So we're going to say we have a right angle right there. We're also going to have what we call here a shared side, and then we're also saying, or actually, you know what? I think we're supposed to be doing point D. I'm sorry, looking here at point D. But anyway, same idea here. You're going to have a perpendicular line right there. You're going to have these distances going on right here, which we're starting out with that. We're given that those two lengths are the same. And then also, you're going to have what we call a shared side right here. So and then forget about this being here for a second. So based off of what we have the one tick, we have the right angle, and then we have the two ticks right there. So by HL, those two triangles that I have made are congruent. Therefore, these leftover pieces right here, these little one ticks right there, are congruent. All right, and therefore that means that point D is on the perpendicular bisector. Once again, it's probably something you don't necessarily need to know. You just need to know the theorem itself, knowing that if a point is equidistant from the endpoints right there, then it has to be a perpendicular bisector, essentially. And I'll show you the problems. The problems are really easy. It makes it sound harder than it is, but it's really not that hard. Perpendicular bisector. So, for example, down here, AC is the perpendicular bisector of BD, find AD. So we're actually using this theorem 5.2 up here. So A is on the perpendicular bisector. So if you want to go mark all that, you can, but essentially all you're going to do is set those two pieces right there equal to each other. And usually it's pretty intuitive to figure out, what pieces you need to set equal to each other. So you'll get negative 3x equals negative 6, and therefore x equals 2. And then, I don't know, they're saying find AD. So if I go plug that back in, that would be 4 times 2, which is 8. And then you're done right there. And that's really all the problems are. They're really straightforward, honestly. Next one right here, I guess. So this one here, I guess, is saying that, B is equidistant from the ends of this segment. Therefore, this has to be a perpendicular bisector. So therefore, these two little pieces right here are the same. So really, with this lesson, you just got to figure out what pieces that you set equal to each other, and that's really it. So x equals 2, and then find AC. Okay, so if I can find AD pretty easy just doing 4 times 2, and that's 8. But since this side is 8, the other side must also be 8, the other segment. So then I guess AC is a total of 16, and you're done there. Okay, same type of problem here. Notice here you got D, I guess, is on the perpendicular bisector. So these two segments right here should be the same. So 5x minus 20 equals 2x plus 4. So we can subtract over the 2x, you get 3x, you can add the 20, you get 24, and then x equals 8. And then what do we find? Find CD, so go plug 8 back in. Honestly, you can plug it into both sides, either side, because these lines should be congruent anyways. But anyways, I guess, 2 times 8? And then plus 4, so was that 16 plus 4? Something like 20. So there you go. It's really not hard to just figure out what you set equal, and most of the times it's going to be intuitive. Okay, another one right here, another theorem about angle bisectors. Once again, I guess erased what was originally on there, so I made it look like just a normal angle bisector. So maybe you did the angle bisector, you got the little cross thing going out here, and then you connected your lines right there. So we're saying that we have an angle bisector. We're going to start out with some random point, we'll call it point D, I guess. And we're going to say, whenever you look at the distances from D to the ray AB and then D to the ray AC, you're going to have those distances right there. So remember, distance between a point and a line, or a point and a ray, those should be perpendicular right there. So I got a right angle going on. Okay, notice also, if this doesn't mess anything up, Notice also you have a shared side going on, and then also we know it's an angle bisector. So if you look at these two triangles that we're making there, it looks like you got two angles and a side, so that'd be angle, angle, side. And that proves that those two triangles are congruent. If those two triangles are congruent, then we therefore know BD is congruent to DC right there. So we can go and write that out in our proof, or in our theorem, I guess. So then it is equidistant from the two, I guess, rays, or some people might say sides, whatever you want there, the two rays or the two sides, if you want to write that instead. So there you go, that's because of angle, angle, side. All right, you also have the converse going on with that right there. So imagine if you say that this distance BD and DC, say you start out with that stuff being congruent right there, and then you have them marked congruent, and then obviously it's got to be a perpendicular line. Ooh, almost dropped my iPad. It's got to be a perpendicular line because remember, distance from a point to a side or to a line should always be perpendicular. And also you're going to have this shared side going on right here with the triangles. Based off of that, that's a special case there. That's called the Hypotenuse Leg Theorem right there. Based off the Hypotenuse Leg Theorem, you can say that D must lie on the angle bisector, because you're going to have those right there. You're going to have the leftover pieces of your triangles being congruent there. So we'll say that lies on the angle bisector. And AD bisects BC. Essentially, you don't really need to know about all the triangle stuff. That's just how you would prove this theorem. That's how you'd walk through the proof. Essentially, you just need to go through and look and figure out what you set equal again. So notice here, you got this point right here. I guess it lies on the bisector. So we know that these angles here need to be congruent. So you'll say 6x equals 2x plus 16. Subtract over, that's 4x equals 16, or x equals 4, and find x in the missing measures / length. So I guess we need to just go plug x back in. Remember, both the angles will be the same. So we'll go 6 times 4, that's 24 degrees, I guess. So both of those angles should be 24 degrees. Or the whole entire angle, I guess you could say, is 48. So yeah, that's really it. Just figure out the missing links here. Notice we got an angle bisector, therefore these two segments must be the same. Oh, whoops. 2, 3 times 4, and that equals x plus 7. Okay, so something like, what, 6x minus 8, and then x plus 7. Subtract over the x, that's 5x. Add the 8, that's 15. So then x is 3. Remember, these side lengths are congruent, so I'm going to plug it into the easiest looking one. 3 plus 7, that's going to get you 10 for both of those lengths there. So you could say CB is equal to BD, which is equal to 10. They're both equal to 10. And that's it, really. I mean, just figure out what you got to set equal to each other and roll from there. Okay, let's see what we got going on here. SQ bisects RST, so angle bisector going on right there. Find QR if UQ is 21. Oh, and UT also, I'm sorry, UT is 28. Now this one's actually kind of weird here because we're trying to find this length here. What was it? Find QR. We're trying to find this length right here. But they gave us a bunch of lengths of this triangle. But remember, these two distances should be the same. So I guess if we can find QT, we're going to be able to find QR. Now, what I notice on this one right here is we have a right angle going on. So if we have a right angle, we have a right triangle. If we have a right triangle, we can always find the third side of a triangle by using Pythagorean theorem. All right, these numbers are a little bit large, so I'm going to get a calculator going here for this one. But essentially, we got the two short sides, 28 and 21. So let's say 28 squared plus 21 squared equals the c squared. So I'm going to go ahead and start punching that out, if my calculator will work with me. So that'll be 1,225 equals c squared. Not sure if that's a perfect square. Oh, it happens to be a perfect square. C is going to be 35 in this case. I guess, too, from the beginning, if you notice here that the sides, they're both multiples of 7. That could help us out there. 35 is also multiple of 7. But anyways, that's all you got to do there on that one. We found C to be 35, so then therefore QR is truly 35 for the distance there. Okay, this next part here, really it's review. It's kind of hard to do the constructions, I guess, on the iPad. I mean, I guess I can show you here real quick. You should know this already because we've learned this. You're going to take your compass, and then you're going to go put some marks, kind of like that, and then you use the same distance, and you're doing this from point B. You're rotating it around points A and B. So you go the same exact distance, so move your compass, and then make two other arcs, and then you connect a line, and then therefore it should be a perpendicular bisector based off of that. And if you want to mark them congruent, you can do that. Also, angle bisector, this is kind of a rough sketch of the steps. Make an arc, use the same length there, centered around the point right there. Then after that, you want to make two other arcs out there from these intersection points. Make sure you use the same distance, and then if you connect, theoretically you got an angle bisector going on right there. So that's a really quick overview. It's not pretty because I don't have a compass, I guess, for my iPad. So anyways, if you need extra help on those, go check out some videos on YouTube. There's probably 100 billion of them. Last thing I wanted to do here, and if you don't care about the proof behind this, I guess you can end the video now, but this is kind of interesting here. It's the mid-segment proof here. So I took a bunch of random points here. I gave them names: x1, y1, x2, y2, x3. I guess that should have been x3. Wait a minute. That should have been y3. I don't know what I'm doing here. So I guess I can fix this up here. Maybe I have it wrong. That should have been y3 right there. Hopefully I wrote it down right, the rest of the proof here. So anyways, the whole idea was I was going to algebraically show with the distance formula that this segment MN is half the segment BC. So first of all, I needed some order pairs for MN. So I went through and did the midpoint formula. Remember the midpoint formula? All that is, oh, it doesn't like me writing up there. All the midpoint formula is an average. So I took the average of these sets of points right there, and you get that for M, and then you find the average of AC right there, and I call that N. Essentially what I went and did with these midpoints is I took those and started doing the distance formula. So I was trying to find the distance MN, so I'm going to use these as my order pairs. Now they kind of look weird because it's not really simplified down. We don't have any numbers, so we can't simplify it down, but essentially what I did is the distance formula, you take the difference between your x's, and then, so that's what I did right down here, and then you square it. And then you go and do all the y stuff. So I went and took the y coordinates, I took the difference of those. Notice here, if you subtract x1 from x1, those would cancel out, and then you're left with just x squared minus x, or I'm sorry, x2 minus x3. Same thing over here with the y's, the y1s will cancel each other out. Okay, after you have that, if you have a fraction squared, it's like squaring the numerator and the denominator, so I kind of split up, I guess, my squares down here, and I forgot to write my squared right there. All right, essentially, you're going to have 4 in both of those denominators, so since I had a common denominator, so you can combine the numerators, so that's what I did on that step right there. All right. Also with square roots, when you're square rooting a whole entire fraction, you can break up your square roots as well. So you can say the square root of that stuff in the numerator over the square root of 4. The square root of 4 is 2 right there. So essentially it's saying take this distance here and then divide by 2. And that's where that came from in the theorem that we talked about. So now I need to just go verify with BC. Hopefully BC is everything in the numerator before we divide by 2. So if you go do the distance formula of BC, you can go and get that x2 minus x3 and then y2 minus y3 right there. And then you go find that. So therefore, MN is 1/2 of BC. And that's kind of your formal proof right there. Anyways, that's the end of the lesson.